So, welcome to the video for the 14th week of the semester, first one, and just if you can hear any background noise, just excuse it. There's just a little bit of noise, but hopefully it won't keep you from being able to hear me. This week I actually decided to not assign any reading from the textbook, and I did this because while there is some stuff in there which is going to correspond to what we're doing, it goes a little further and deeper than I really want to, and I think that the level of depth that it gets to might just end up being distracting. So I'm just going to teach you myself, but if you are at all interested, you could look. If you want to kind of further yourself and stretch yourself and see what I'm talking about, this is kind of the stuff in page 221 to 228. All right, so there are some stuff with like the little I vectors, like the unit vectors. You'll see a whole lot of sigma, all sorts of things, and you'll see like the angled roller support and stuff like that. And frankly, we just don't need to go that far. So that's why you're not missing out if you didn't read anything this week. Now we are going to take a few things that we've learned about. So we have done things like sum of all forces. We have done sum of all moments, sigma F, sigma M. We have talked a lot about reaction forces and also reaction moments. Like that was the whole discussion of the degrees of freedom. Remember that there are 3 possible reaction forces. There are 3 possible reaction moments when you're in 3 dimensions. That's when you're in 3 dimensions. When you are in 2 dimensions, there are actually only 2 possible reaction forces at most, and only 1 possible reaction moment at most. Okay, this is all just stuff we've talked about, but we're going to kind of put it all together today to do fully finished free body diagrams. Fully finished free body diagrams. All right, that is the point of today. And the only way to do this is to practice it, to jump on in. So I have about 5 or 6 planned for you. And please do copy these into your notes. I'm really trying to give you the template of what to do for the assignment this week and for what follows. In the second video this week, I'm just going to give you slightly more complex examples. These first ones today are going to be very straightforward. All right, so I told you guys I just built a table, a kitchen table. I posted some photos. I'm pretty pleased, pretty proud of it. And let's think about my table. My table is completely symmetric. We're looking at it here in 2 dimensions, of course. Okay, no 3D stuff today, just 2 dimensions. My table is perfectly symmetrical. Actually, if I get really detailed, it kind of has like some sort of interior supports, and then there's a kind of a joist that runs along the whole length of it. That's a little bit more accurate. Let's make up a mass. Let's say my table has a mass of, I don't know, 40 kilograms, 40. And let's make up some other stuff. Let's say that my table has a length of 2 meters. In actual fact, my table is 8 feet long, so it's closer to 3 meters, but we'll call it 2. All right, so now we're going to draw our free body diagram. And let's start to show the things that we talked about. We talked about 4 things. Weights, applied forces, the normal / reaction forces, and the friction force. So let's start to take care of those one by one. This is all stuff from last week. First of all, there is a weight force. Now, because my table is symmetric, that is going to be right there in the middle. In fact, we could say 1 meter. I could even show that. Maybe I will. 1 meter in from the end. Now, what is the weight? I'm going to use just round figures today. I'm going to say the weight is 400 newtons. If you don't know how I got from 40 kilograms to 400 newtons, then you have not been paying attention. Now, let's see what's next. Applied forces. Okay. No one is pushing on this, at least no one we've been told about. No one is sitting, standing, interacting with this in any way. There's no ropes tied to it. So this thing is just sitting there. This is really easy. So there are no applied forces. Now the normal forces. How would we describe what is the support type? How are these legs, the parts that are in contact with the ground, and by the way, notice I didn't draw the ground because this is a free body diagram of the table. So we get rid of the rest of the universe, including the ground. What kind of support type are these legs? Is it pinned? Is it fixed, like a welded, cemented thing? No, it's not. These legs are what we call simply supported, the simplest type. This is like the tent pole. It's like the crate just resting. It's just simply sitting on the ground. So the simply supported type, okay, SS for simply supported, only has one possible reaction. And it's this one here. And I'm just going to say, because I know these are the only ones, I'm just going to say R1, R2. Okay? Those could be different, so I do have to give them some kind of different designation. R1, R2. I don't know what those are, by the way, but I start by showing everything that I know could happen. Now, with simply supported, there is no reaction moment, there is no sideways reaction force. And then lastly in our list of things to show is friction. Okay? Again, no one's really pushing, it's not going anywhere, there's no sideways activity, so let's just forget about friction. It's not really necessary. So this is everything. This is the free body diagram. But what we're going to do today is we're going to take this a step further from last week, and we're going to solve for the unknown reactions. And I actually really enjoy this. This is one of my favorite topics. So if you can hear the enthusiasm in my voice, that's why. Now, first thing I want to say is I bet that this one is intuitively solvable. All right. You can look at this thing and you can say, man, this thing is symmetric. There's 400 newtons of weight, 2 reaction forces. I know what they are. They're both going to be 200 newtons pushing back up. And by the way, I'm treating those 2 legs, I realize the table has 2 legs at each end, but because we're analyzing in 2 dimensions, we kind of smush those 2 legs together. We just think of it as there's 200 newtons at each end. Now this one is intuitive, that's why I started here, but let's go through the actual process that we would do for a more complex, non-intuitive, one that needs analysis. The idea is that in 2 dimensions, there are 3 equilibrium equations. Okay, this is really important. Okay, this is the point of today. That in 2D analysis, which is all we're going to do, there are 3 equilibrium equations. And those 3 equilibrium equations are these. The sum of all forces in the horizontal direction, the sum of all forces in the vertical direction, and the sum of all moments. And let me do the standard sign convention. Okay, so I'm going to great pains. I'm showing the positive direction in front of each one. Our textbook does the exact same thing, and just for the sake of redundancy, I'm also just going to put a little sign convention diagram right here. Okay, very important that we know which way is positive, which way is negative. One more thing I'm going to do, when it comes to the moment sum, moments have to be summed around a particular point. Okay, with forces, it's just like they're either vertical or horizontal. If they're not either of those, then you break them down to components and then you use the horizontal vertical components. But with moments, because a moment is a force times a distance, you must define a rotation point which you measure all the distances back to. Now, this doesn't have to be a real point of rotation. You don't have to actually get motion to use this. You just got to pick a location and then you sum the moments around that location. So I'm just going to pick this leg right here. Once again, I don't expect the table to rock up on those legs at the left or to rock downwards into the floor or anything like that, but I do just have to pick somewhere to measure distances from. And so because I called that like R1, like that's kind of like, let's call that location 1. Okay, I could even label that. This is location 1. And it's fine if you do like location A or B or C. Just pick something that's not going to be used anywhere else on the diagram. Location, 3000. But just use it, okay? So this is the one that I'm using right here. I think you'll see more what I mean in a second. Okay, let's work through these. In the horizontal direction, we list off all the forces and we know that they will all equal 0 because this table is not accelerating anywhere. Now, what horizontal forces do we have? In this example, we actually have nothing. So I list nothing. There's nothing left, nothing right at all. Not applied, not reactions, nada, no friction. So that actually just all takes care of itself. That's it. That one's done. Let's move on. That one will become much more important in other more complex analyses. Okay, in the vertical, I have R1 going upwards. So I make sure that it's positive R1, plus R2, also positive because it's also pointing up. I defined up as positive. And now I'm going to do minus 400. The minus because the weight is down. And then, oops, I forgot. I also do equal to 0 because I know that everything is balanced. Whatever happens, it is all balanced because the table is not accelerating. Now, let's leave that for now. Let's do the moment sum. Okay, I'm going to put the 0 first just to remind myself. All moments equal 0 because the table is not rotating. It's not accelerating in rotation. So what I do now is I consider all the moments that are acting. And remember, the moment is force times distance. Don't ever forget that. Super important. The moment is force times distance, and those must always be perpendicular to each other. I've drawn that little sketch many a time. Okay, so the R1 force, the R1 force, that does not create a moment. We're kind of going to move from left to right here. The R1 force does not create a moment through that red rotation point, that location that I marked with a 1. It doesn't cause a moment because it is shooting straight through it. So there is no offset distance. Okay, the distance is 0. It's on the rotation point. So I'm not even going to write that in the equation. I'm not going to write R1 times 0. I could if you really want to, but there's just no point. We'll leave it out. But as I keep going along, the weight force, which is 400 newtons, is multiplied by the distance. And I'm talking about this distance here, because this distance is perpendicular to that weight force. And that is a distance of 1 meter. Okay, so that weight of 400 times that length of 1 meter, that is the first moment that I need to consider. And this one here, I'm going to do this then undo it. This moment is acting in this direction. Okay, it's like swinging in a clockwise way, if it could, around that red point. Okay, let me show that again. It is revolving around that red point, if it could. Obviously it can't, but that's the way it's trying to do it. So that direction, according to our sign convention, is negative. It's opposite to that. So I must put a negative in front of that moment. Now I move along. The next one is R2. Now R2 is pointing up, and it is offset by this distance, which is the full 2 meters. So this one is going to be multiplied by 2. Okay, force times distance, R2 times 2. And this one is trying to swing that away around the red point. That's a positive moment. So we are going to make sure that one is positive. And that's it. Only those two forces are creating moments around that point, because the R1 is shooting straight through that point. So what we have here in the end is we actually have two useful equations. We have the Fy equation, the vertical forces. That's a useful equation. R1 plus R2 minus 400 equals 0. That says something. Unlike 0 equals 0, that says nothing. And then we also have 0 equals negative 400 times 1 plus R2 times 2. We have two useful equations, and we have two unknown forces, R1 and R2. Now here's the basic rule of math, is that if you have two equations and two unknown things, that is the perfect situation. You can solve for those two things most of the time. There are some exceptions, but in general that's true. If you were to have three unknown equations, you would need three useful, sorry, did I say equations? If you had three unknown forces, you would need three useful equations. Okay, that's the rule of algebra. You must have as many equations as you do unknown things. Okay, so this is good. We can do this. And I might just move the screen a touch. So let's put these together. I'm just going to kind of carry the working down here a little bit, just clean it up a little. R1 plus R2 equals 400. You see I added 400 to both sides. And over here, if I, again, kind of rearrange things a little bit, I will get, let's see, 2 times R2 equals 400. Okay, same deal. I added 400 to both sides and just switched the left and the right hand side, and I put the 2 in front of the R2. No great changes, but I hope you can see where this is going. Hope you remember your simultaneous equations. I don't know if they call them that on this side of the world. That's what I was taught to call them, a system of equations. I think that's what you guys call it. So what I'm going to do here, I need to eliminate a variable. So what could I do? Let's see, I could multiply this whole equation by 2. That would give me 2R1 plus 2R2 equals 800. Okay, this is the kind of stuff that you learn usually in pre-calc, maybe algebra 2. And the reason why I did that is because now we can subtract one equation from another. And that will give us this. We just use the rules of algebra. 0 minus 2R1 gives us an answer of minus 2R1. 2R2 plus, minus 2R2, remember that negative carries through, that is going to zero those out, okay, that will disappear. And then 400 minus 800 gives us negative 400. See what I'm doing there? I'm subtracting vertically. I think 9th and 10th grade students, like usual, will have the most trouble following what I'm doing potentially, but I'm just subtracting these algebraic terms. I'm treating R1 and R2 as algebraic elements like X's and Y's and Z's. And and I subtracted 0 minus 2r1 to get this first term, 2r2 minus 2r2 to get nothing, and then 400 minus 800 to give negative 400. Okay, that's my sum right there. And then I keep the working going. I would divide by negative 2, and that would leave me with positive 200. Okay, R1 has been solved. And then from there, I use that answer and I re-substitute that into maybe like this original equation right here. If R1 plus R2 equals 400, but R1 equals 200, I can sub that in and it's going to take care of itself. Subtract 200 from both sides. Look at that, my goodness. I have two answers right here. R1 is 200, R2 is 200, and that is exactly what we expected was going to be the case. Because it's a symmetrical table, it's a 400 Newton table, so we would expect the 200 to be there on both sides. Alright, if that seemed overwhelming, I'm going to do this now about 3 or 4 more times with different situations. And we'll get really, really used to it. So let's do this. Let's grab all of this again. How about all that? There we go. And we're going to copy that, yep. And let's go off to the side. Oh dear. Hold on. I don't know how to paste with this app. Let's see. Oh, look at that. Paste. There we go. Alright, I'm sure that was completely worth it. Okay. Oh, well, back to 100%. There we go. Okay, totally worth it. Alright, now this time I'm going to change something up a little bit, just to make it more interesting. We are now going to stand a person on the table. Okay, whoops. Oh boy. Okay, we're going to put a person on the table, and this person is going to have a mass of 60 kilograms. Okay, kind of an average-ish adult or teenager weight. Let's see. Okay, so let's march through these things again. Oh, you know what? I should tell you. We're going to put the person right here. And again, if their mass is 60 kilograms, that means their weight is 600 newtons. And we are going to place the person exactly at half a meter. Okay, so maybe someone is standing on the table to like screw a light bulb into the ceiling or something like that. Maybe they're sitting on the table. I always tell you not to do that at school because obvious reasons. Putting your backside where people eat their food is disrespectful. That's the reason why. But this person, let's say, is standing. That's way better. And they stand on the table with all their 600 newtons, and let's just quickly check through these different things. We're drawing a free body diagram. We have the self weight of the table is right there, the 400 newtons. We have the applied force. We have one now. We have a person on the table. That's an external applied force. The normal or reaction forces is the R1 and R2. And then are there any friction forces? Nope, not in this case. Nothing is trying to slide or slide in, so no friction. And we are going to go through, maybe I'll do it over like here. We're going to go through with all of those different equilibrium equations. We're going to say, we're going to start off with the horizontal one. Then we're going to do the vertical one. And then let's do the moments. And again, let's just, for the sake of simplicity, let's sum them around that location 1 in the exact same way. Now, because the table's not going anywhere, we can actually just put in all those zeros first. We know that these sums must equal 0. But what is in these sums? Okay, horizontal forces, Fx, sigma Fx. Are there any horizontal forces? No, there are none. Once again, this makes the Fx equation useless for our purposes. We cannot use it to solve things. It is simply irrelevant. It is unhelpful. I guess it does convey information. It says there are no horizontal forces. That's helpful. The vertical forces, Fy, sigma Fy, we now have R1 plus R2 minus 400 minus 600. We have two downward, negative is downward, forces right now, as well as the upward R1 and R2. Okay. Now the sum of all moments, here we go. We now have, maybe let's quickly do the ones we had before. We had the negative 400 times 1, and I am going to show the times 1. It just helps the brain. Force times distance. We had the positive R2 times 2. That didn't change. But now we also have a negative 600 times 0.5. Okay, that distance is the one I want. Okay, that 0.5 just horizontally across from the rotation point. It doesn't matter, by the way, that the person's applied force is like slid up away from the rotation point. It's much more, what's more important is that line, okay, that force shoots down, if you like, in a slidable line, and then there is still that 0.5 perpendicular distance. That is how that is done. Okay, so we have the 3 forces this time, and notice that I kept R1 and R2, even though we solved for them in the previous problem, we found they are 200 and 200. We can't use that this time. Those forces are actually going to change. They're very malleable. They adapt to whatever is happening. So that's why I couldn't just jump in and say, oh, 200 and 200. We don't know that. You will see. They will be different. Let's go. I'm actually just going to pull that across. Just make a little more room. Oh, you're going to do all sorts of crazy things to me. You know what? I like them where they are. I think I'll get rid of that. There we go. All right, let's do some work on these. So let's clean the stuff up. Here's some useful equations. We have R1 plus R2 equals positive 1,000. Hope you can see how I did that. I added 400 and then added 600 again to both sides. Totals up to 1,000. On the other side of things, we have 400. Oh wait, I should. Let's do 2R2. I add the 400 to both sides. This is just like last time so far. But then I also have 600 times the 0.5, which makes 300. I add that to both sides. So let me actually just go ahead here and write 700 total. Okay, 400 plus 300 gives me 700. They were both negative, but I moved them both over, so that's why we get positive 700. And as you can see, we have a different set of equations than what we did before. Okay, before we had 400 and 400. Now we have 1,000 and 700. So that will give us a different result. But I'm going to do kind of the similar process. I'm going to multiply those by 2, which will give me 2R1 plus 2R2 equals 2,000. Once again, I will subtract those from each other. 0 minus 2R1 gives me negative 2R1. 2R2 minus 2R2 gives me nothing, they cancel. And 700 minus 2,000 gives me negative 1,300. That is my result. I divide both sides by negative 2, and I get R1 equals positive 750. No. Sorry, positive 650. Okay. 1,300 divided by 2 is 650, and then the negative 2 got rid of the negative in front of it. So that is my R1. And then again, I'm going to substitute, I'm going to feed that into this original equation. I get R1 plus R2, I'm just going to rewrite it again, equals that. But I know now what R1 is. I can sub it in. I subtract 650 from both sides, and that leaves me with 350. Those are my two answers this time. R1 is 650 newtons, R2 is 350 newtons. So you see, having a person standing on the table asymmetrically to one side results, as you would expect, in a bigger reaction force on that side. In fact, I might even want to kind of extend that out to show that's a bigger force. That leg has to be pushed harder upwards by the floor than does the R2. In fact, interestingly, this is quite interesting. Well, no, sorry, I was about to say something. I would have been wrong. So we had 200 and 200, and now we have both legs actually carrying more. Okay, like they both pick up the extra weight of the 600 Newton person to some extent, but more so the leg that is almost underneath the person. All right. So far we're at about half an hour. I want to show you another example. Let's do a completely new one. This one is a diving board. And the reason why I'm going to do a diving board is because then we get to use some of those different constraints that we have been talking about. At one end of the diving board is a pin joint. Okay, the pin joint, like a bolt through it or something. It is free to rotate, remember, with a pin joint, but it can't slide up, down, left or right. And then, let's see, we will also put just a little, I'm putting a little triangle symbol. That's like another way of showing either a roller or a simple support. It doesn't actually matter too much in this case whether it's a roller, like a rolling thing that it can roll across on like a little wheel, or if it's simply support. I think in actual fact the diving board I last saw at the, where is it, Ennisbrook Tennis Club, I think that actually had a roller under it, but they took that away a couple of years ago. Anyway, so okay, now let's make up some numbers here. I'm going to say that the roller or simple support is 4 feet along. The total length of the diving board is 10 feet. And I will also say that the diving board has a weight of 40 pounds itself. Okay, it has a weight 40 pounds. And remember, as soon as you start hearing me talk in terms of feet and pounds, you know that you're in the US customary system. And that means that if I'm saying pounds, that is already the weight. that is not the mass. You don't have to like multiply this by 9.8 or by 10 or any other tricks like that. In the US customary system, people really just talk in terms of the weight. Mass is measured in slugs and no one uses them. So watch out for that little trap. It's gotten quite a few of you quite a few times. All right. I think we have everything we need. So let's start to... no, actually, you know what? I'm going to add one more thing too. So the weight of the board itself is 40, but I'm going to put a person. Let's use P for the person's weight. A person of weight 50 pounds. And this person is going to be standing 2 feet in from the left. Okay, so let's start to sketch these things. It's a free body diagram. So we start by showing the weight force. We can very safely show that in the center. Very, very safe assumption. 40 pounds. Okay, now that is at a distance of 5 feet. If it's a 10-foot diving board, we put that weight halfway along, 5 feet. And then the person, okay, I'm sorry. So we start with the weight and then we move on. The second thing in the free body diagram is all the applied loads, if there are any. A person standing on something, just like with the table, that is an applied load. I'm going to put that person right here. I'm going to use a bigger vector because they're bigger than the 40 pounds. They are 50 pounds and they are 2 feet long. You know, if I'd thought about this and used the squares, I wouldn't be drawing all these measurements, but I didn't, so it's okay. I was actually pretty close. I count 9 squares. Oh well. Next time. What else? Okay. Third thing to show on a free body diagram is the normal forces or the reaction forces. Now in this case, we will have three reaction forces. A pin has 2. A pin, I hope you can see that's an arrow. A pin has the, let's call this R1Y. Okay, it's at like location 1 vertically, so hence R subscript 1Y. A pin joint also can resist horizontally, so we show R1X. Alright, if someone is tugging left and right on this, or if a person like springs off and pushes sideways, that pin joint will resist that. So we show that potential reaction force. And then we have this simple support or roller. Let's call that R2Y. So that'll be, in other words, location 2, like a special location number 2, and it is vertical. A simple support or a roller cannot resist sideways. It doesn't get a horizontal one. It just gets the vertical one. Okay, and then lastly in our list of things is friction. Is there any friction at play here? Nah, friction's not really going to matter. Nothing is sliding or trying to slide here. Okay, let's do our equilibrium equations. The sum of all horizontal forces will be 0. The sum of all vertical forces will be 0. And the sum of all moments will be 0. And I am going to sum my moments. You know, I may as well just pick that location 1 again. I kind of like it. Okay, location 1 is this pin. Okay, that's why it's labeled with R1X, R1Y, and I'm going to pick that as the place around which my moments are summed. You don't always have to choose the leftmost location, but it often is just kind of convenient. It's actually best really to choose a location which has a lot of forces, like as many forces as possible shooting through it, because then you don't have to count those moments. Okay, now let's start to list them off. Horizontal forces, do we have any? We do actually. We have R1X, and it is pointing in the positive direction. Okay, so we list that. Vertically speaking, we have R1y is pointing in the positive direction. We have we have R2y pointing in the positive direction. We have negative 40 pounds for the self-weight of the board itself, and we have negative 50 pounds of a person standing on the board. Notice that the distances, the location of the standing doesn't make any difference for the vertical force sum. But it does for the moments. Here we go. For the moments, R1y and R1x are not going to cause any moments because they are shooting through the pin itself. So they can't cause a rotation. So we don't need to list those, but we absolutely need to list a negative 50 times 2. It is negative because the 50 pounds is trying to swing around and around in a negative direction around that pin joint. We are going to list R2y. It is going to be positive, and it is going to be times a distance of 4. It's positive because it goes that way, which matches with the positive direction. And then we're going to have a negative 40 pounds times 5 feet. Okay, again, last time I'll show this, negative because it is trying to go around that blue rotation point opposite to the sign convention that we picked. And the 5 feet comes again from the halfway point, halfway of 10, half of 10 is 5, that's all. Alright, I think we're ready to start putting all the bits and pieces together. First of all, we actually have an answer right here. R1x equals 0. You don't need to do anything else there. That is telling you that this is 0 newtons and nothing else needs to be done, which makes sense. If no one is pushing sideways, the reaction force doesn't rise to do anything, doesn't have to rise to meet that. Really, arguably, I could actually erase that force right now because a vector of length 0 just is invisible, it vanishes. But we'll just leave it there so we know that we actually did take it into account. Okay, the other ones, let's clean this up a little bit. Let's do R1y plus R2y equals positive 90. Okay, hope you can see why that is the case. And then the moment sum, let's rearrange that a little bit, let's add some things together. Let's say R2y, notice I'm lining that up, equals, what have we got here? 50 times 2 is 100, 40 times 5 is 200, so that makes 300 total over the other side, 300. Okay, just some quick, basic algebra there. Now this is kind of, oh, I forgot something. R2y was times 4. Sorry, almost forgot that. This was going to be very quick, but it was not to be. I'm going to multiply this whole equation by 4 to give me 4r1y plus 4r2y equals 90 times 4 is 360. Okay. And now I can subtract one from the other. This feels very similar, doesn't it? And it won't always be exactly the same, but it happens to be so right now. 0 minus 4r1y is negative 4r1y. 4r2y minus 4r2y makes them cancel. That was the whole point of multiplying the equation by 4. And 300 minus 360 gives us negative 60. We divide both sides by the negative 4 and we get R1y equals positive 15. Awesome. R1y equals positive 15. By the way, the positive here, the positive means that I picked the correct direction. I actually guessed that R1y was going to point up. I didn't really know if it would or not. It can actually be pulling down as the diving board tries to like imagine the diving board tries to kind of flip over the roller into the water. If it were doing that, R1y would actually have to pull down to keep that from happening, but it didn't. I guessed an upward direction, and the positive 15 tells me that my guess was correct. It actually doesn't mean positive in terms of up. It means positive in terms of confirmation in this case. Now, if R1y equals 15, I think I'm running out of room. Yep, I am. So I'm just going to work over to the right-hand side here. If R1y equals 15, I am going to substitute that into this equation right here. R1y plus R2y equals 90. I pop it in, I get 15 plus R2y equals 90. Subtract 15 from both sides. R2y equals 75. And there I go. 75 newtons, okay? So there's 90 pounds of total downwards force, 50 plus 40, and between those two supports, the roller, the simple support, is actually taking almost all of it. And I guess that kind of makes sense because the 50 and the 40 are kind of like on either side of it. So, I guess that makes sense. And the R1y is just resisting a little bit of 15 newtons, which is, oh, what am I doing? Did anyone catch that? This problem is in pounds, but silly me, I'm writing newtons everywhere. Sorry, those should have been pounds. Okay, that is that problem. Now I'm going to do one more situation here. Let's do the diving board one more time. But this time, the person walks all the way out to the end. And this time I will use, I'm going to count 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. I'm not going to draw any links this time. There's our little hingey hinge. Where was that? 4 feet long. And let's put our person almost all the way to the end. Okay. 50-pound person is 1 foot from the end, or 9 feet long. They're almost ready to jump. We still have our self-weight right there in the middle. And we list our unknown reaction forces. We have R1y, we have R1x, and we have R2y. Alright, so that is everything. All we did was just change the location of the person. The person walked out, they're ready to jump. Very exciting. And we list off all of our stuff again. I'm just going to do it over here. We still have the sum of all horizontal forces we know is 0. Sum of all vertical forces we know is 0. Sum of all moments around location 1 is going to be 0. I know they're all 0 because nothing is accelerating, because we're doing statics this year. Okay. Add up all the horizontal forces. What are they? Just the one again. Just the one, which, as we said last time, gives us our answer already as to what it is. Gee, I love just doing things by grid squares. My diagram's way cleaner. Adding up the vertical forces, we have R1y plus R2y minus 40 pounds minus 50 pounds. And notice that actually didn't change. The person walking out doesn't change how much the Earth's gravity is pulling them down. And that's all the vertical force sum takes into account, is just gravity down, things back up. That's it. Walking around, doesn't change that. The moments, we don't consider a moment from R1x or R1y again, because they shoot through the pin itself. But we do have the positive R2y times 4. We have still the negative 40 pounds times 5. And now we have this crazy one. The person walked all the way out. It is still a negative moment because it still wants to do this around the pin joint. But it's now 50 times 9. 9 feet. We're talking about this 9 feet right here. Alright, let's play with these a little bit, as we have been doing. We have R1y plus R2y equals 90. Again, like I said, nothing changed there. And then we have 4. Oops, let me keep those lined up. 4R2y equals, now what do we got here? 40 times 5 is 200. 50 times 9 is 450. You add those together, you get 650. It's quite a lot. I'll do my exact same trick. Multiply both sides by 4. Gives you 4R1y plus 4R2y equals 360. We will, once again, subtract those from each other, giving negative 4R1y, giving nothing there. It cancels. 650 minus 360, that makes my brain hurt just a little bit. But it is 290. You were probably way faster than me there. Did I get that right? I think I did. Okay. And then we divide both sides by negative 4. Now this is interesting. Let's see, what's that? Divided by 2 is 145. Divided by 2 again. Trap. These are more complex numbers than I wanted to do. 50, I think it's 72.5. I'm just going to quickly do that in the calculator. Hold on. I think I'm right. Yep, 72.5. Okay, and notice it is negative. This is different. In the previous examples, all the ones we've done actually, when we divided, we were dividing and we'd end up with a, see this, we'd end up with a positive number. But not what's happening here. We divide and we end up with a negative number. So what that actually means, that is a signal to me. That is saying my R1y direction was incorrect. It wasn't pointing up after all. It was actually supposed to be this way. It is 72.5 pounds, but it should have been down. And then again, I'm trying to get through this for time's sake. Let's finish all of these. R2y equals 90. We're subbing in the negative. Okay, so watch that negative. So we're actually going to add 72.5 to both sides, which is going to give us 162.5. It's positive, which means our assumed direction was good. And that is a very significant. Notice what happened here. Pretty weird. Person, 50-pound person, stood nicely between the pin and the roller. And you got 15 plus 75 pounds. Like pretty moderate. Not much more than the weight of the person themselves. Now, the same person walks out to the end. Look what happens. Suddenly the pin on the left has to pull downwards. That was different. and with a force more than the weight of the person themselves. And then this roller is more than 3 times the weight of the person themselves, pushing back up. So that's really straining. So what this tells you, actually, we're going to do this later in the year, but what this tells you is that this board could actually break around that spot right there, where that peak force of 162.5 pounds is. Or at least it tells you that if it is going to break anyway, it's going to be right there. And this just shows you the power of moments, which is actually a book on my shelf, The Power of Moments. But the power of moments is that someone with a small force can magnify their force to create much larger forces, apparently for free, just by shifting positions. It's the whole principle behind like pry bars, behind screwdrivers and wrenches and things like that, behind the jack that puts your car up into the air. Small forces done right can create very large forces, apparently for free. Okay, we're going to leave it there. That's a 56-minute video so far. As I say, the next video is going to be just more complicated examples of this, but nothing fundamentally different. So I hope that your brain is cooking and that you can get into that assignment straight away and leave some comments on the discussion board as well. Thanks, guys. You're doing a great job. Keep it up.